my name is Martin Derlet. I am a PhD student at the German Research Institute for Cyber Defense. Today, I want to tell you about a project I've been working on with my supervisor, Stefan Brunthaler, that aims to bring us toward efficient and verified virtual machines for dynamic languages. When a program in a dynamic language gets executed, it is fed to a virtual machine which compiles it on the fly to bytecode and interprets each bytecode instruction one after the other. This execution model is very convenient, but it tends to be slow, so virtual machines are often optimized with just-in-time compilers. These compile the bytecode at runtime to input-specific machine-native code and allow to achieve near-C performance. But just-in-time compilers are very complex programs, and virtual machines' code bases now contain millions of lines of code. As can be expected, this increase in complexity came at the very high cost in correctness and security. So we wondered, could one use the ComCert technique and formally verify the correctness of virtual machines with just-in-time compilers? We are rather skeptical about that. You see, compilers are relatively simple programs that work as a pipeline, while modern virtual machines, on the other hand, work more like a huge and complex state machine. The other problem is that they constantly modify their own program at runtime, and it's not entirely clear how to formally reason about such self-modifying programs. And worse, even if it was to be done, the mere nature of dynamic code generation is a security liability. You see, the first step of most attacks is to get the victim's processor to execute some code under the control of the attacker. This means that every single function that gets just-in-time compiled could be the payload of such an attack. We believe that a more promising strategy is to add simple and effective optimizations to verified bytecode interpreters. So we specified 3 bytecode languages that incrementally support more optimizations. DIN is the baseline that we extend with a type-based optimization called inline caching to form Inca. We then extend it again with a data representation optimization called unboxing to form UBX. For each language, we define a realistic small-step operational semantics, a simple compiler, and a bisimulation relation that ensures compiled programs exhibit the same behavior as their original programs. We mechanized our formalization in Isabelle Hall and ended up with a total of around 6,000 lines. We made extensive use of Isabelle's locales to abstract over implementation details not really relevant for the optimizations. So let's start with DIN, which is a simple stack-based interpreter for dynamically typed languages. All support data types are gathered in a tagged union of dynamic values. We can see it at play in this small example program that performs the conversion from Fahrenheit to Celsius. At the beginning, the operand stack is empty. When the virtual machine executes the load instruction, it fetches the number 65 from dynamic memory and pushes it onto the stack. Notice that the constructor keeps track that it is a floating point number. The next instruction pushes 32, and the next instruction is a subtraction operation that pops the 2 topmost operands and pushes the difference. The execution continues until the final result remains on the stack, at which point it is stored back into dynamic memory. Operations are implemented in a fashion akin to the following. When the virtual machine encounters an operation instruction, it calls an evaluation function with the specific operation and the arguments taken from the operand stack. The eval function first performs a pattern matching on the operand and then continues with a pattern matching on the arguments. When the type of both arguments match, the calculation is performed. In this example, with a float and integer, 6 type checks were necessary. This means that the case on the 4th line will always be slightly slower than the case on the 1st line. Sure, we can tune the order for often occurring cases to be higher up the list in the pattern match, but this would only move the problem around. The idea of inlining is to have multiple equivalent versions, each of which using a different permutation, especially efficient for a specific type. So in this case, for arguments of type float and int. Formally, we use a locale to abstract over the set of operations and their implementations. Locales are Isabelle's way of expressing an interface akin to a ML functor or a dependent record. All blue types are abstract types, and all fixed parameters are abstract function declarations. This is where we find the eval function, whose implementation we just looked at. A second locale introduces the abstract set of inline operation, the evaluation function for inline operations, and a mapping from one set to the other, as well as its inverse. Finally, we state a certain number of assumptions on these abstract functions. Now, we extend the DIN bytecode language with these inline operations to form the Inca language. Executing our Fahrenheit to Celsius converter in Inca should give a good intuition of how inline caching works in practice. During the first pass, the virtual machines observes the encountered operands and rewrites the program to use the inline operations. On the first pass, we see that Inca was slower than DIN because it had to pay the upfront cost of optimizing the program. On subsequent passes, the inline operations are directly used, and the Inca virtual machine then needs less type checks and performs better. The compiler from DIN to Inca trivially lifts all instructions. To prove soundness of this operation, we prove that there exists a bisimulation between a program and its compiled version. Completeness can be reduced to the fact that the compiler is a total function. Now, while inlining reduces the number of type checks in pattern matching, the unboxing optimization tries to avoid pattern matching altogether by bypassing the dynamic constructors, which we then call boxes, and whenever possible, working directly with the machine native values, which we refer to as unboxed. In this example, the division operation has direct access to the argument x and y of type float and int, respectively, and it does not need to box its result in a dynamic value. We then extend Inca with unboxing to form UBX. Let's see what this looks like for our Fahrenheit to Celsius converter. This optimized version of the program expects to load a floating point number from memory. When executing the loading instruction, the dynamic value has the expected type, and the number 65 is unboxed and pushed onto the stack. That is, without a df constructor. Then the next instruction pushes an integer, and now the unboxed operands are passed to the subtraction operation. Execution continues until the last instruction boxes the final result and stores it back into memory, that is, with a dynamic constructor. In this case, we were able to perform the full computation with only one dynamic object inspection and for the initial value and one allocation for the final result. The compiler from Inca to UBX lifts instructions from Inca to UBX and performs a single pass optimizing abstraction interpretation. Compilation is sound, as in, if it succeeds, there exists a bisimulation between the program and its compiled version. But it is incomplete because the abstract interpretation fails for some nonsensible programs, and also because the exact algorithm that we used is too weak to handle some valid programming patterns. So, in summary, we covered 3 bytecode languages that implement 2 speculative optimization. DIN is our baseline. Inca implements inline caching, which replaces operations to minimize the number of type checks. And UBX implements unboxing, which replaces as many instructions as possible and changes the data representation to reduce the number of type checks even further, and reduce the number of dynamic values in allocation requires. Our formalization was mechanized in Isabelle, where we specified the realistic small step operational semantics for each of these 3 languages, while trying to keep multiple details abstract through Isabelle's locales mechanism. The formalization will be available under this URL in the next version of the archive of formal proofs. So, thank you for your attention and have a nice day.